Okay. So, in this presentation I want to talk about interface stress using molecular dynamics. We will start with a little bit of history. What is interface stress, how people came to realize that there are these quantities, and once you know what it is, you will also realize why or how difficult it is to measure them. And even atomistic simulations are more recent, because the formulation to evaluate them came a little bit later, or formulation was available a while back, but people have not realized or have not used it to do simulations. And so, I will show the formulation and I will show the more recent development where this formulation is used to evaluate interface stresses, and then we will show some MD simulations we have done to evaluate this quantity. And there you will see that the first step is melting point calculation, second step is elastic moduli calculation, both of which you already know. So, then what is more is what partly I will do today. There is also one piece that I will keep for later, which is a little bit technical, but if you start doing simulations, it becomes essential that you know how to do these things. So, we will end with a summary. So, we want to look at stressed solids which are in equilibrium with fluids, and this is a very old problem. If you go to a geology department, for example, lots of minerals are under stress and they are always in contact with their own solution. It is not their melt, but it is their solution. So, lots of activity is there, and the subject itself is very old, as old as Gibbs at least. So, he says the conditions of internal and external equilibrium for solids in contact with fluids with regards to all possible states of strain of the solids. So, that is what he was interested in, and this is there in his on the equilibrium of heterogeneous substances. This is 1876. Okay. Important point to note is that Gibbs time it was not clearly established that solids can change state by diffusion. Okay. So, but there is still, and Gibbs was a mechanical engineer by training. I do not know how many of you know, his PhD thesis was on some gears or something he wrote. But then he moved, and vector analysis, the way we use today, we owe a lot to Gibbs, and of course, in materials thermodynamics Gibbs is there all over the place. So, 1876 there was this problem, okay, you have a solid in contact with a fluid, and how do we look at the equilibrium. So, this is the question. And then Bridgman, so nearly 40 years later, writes in an article in PhysRev 1916. So, he is also interested in this problem. I mean, some of you might know Bridgman. He is famous for his crystal growth technique that bears his name. The question at issue was, what is the effect on a transition or melting point of unknown extra stresses not hydrostatic in nature? Okay. It was surprise to me after a careful search to find that this problem has received very meager attention, he says. This is in 1916. So, he is also interested in knowing how the transition temperatures change because of non-hydrostatic stresses. Hydrostatic stresses means like pressure. Okay. So, solids are the ones which can support non-hydrostatic stresses to some extent. I mean, solids also flow, we know that, but broadly, largely they can support. Fluids, liquids and gases cannot. So, he was interested in this problem, and 40 years after Gibbs, he still finds that there is not enough in the literature for him to. So, this paper is written to address some of those concerns. And then Kahn in 1979, we are already 40 years after that. So, he writes that 100 years ago Gibbs developed a thermodynamics of both fluid and solid surfaces that included such topics as adsorption, heat and mechanical surface effects, curved surfaces, you saw Gibbs-Thomson, we discussed this morning, homogeneous and heterogeneous nucleation, stability and even grain boundaries. Since this monumental paper, almost everything that has been written has been within the framework of what he bequeathed to us. Some of these papers are easier to read, others are easier to apply, but few match the rigor, logic and scope of the original. This is what Kahn says. on a paper on thermodynamics of solid and fluid surfaces, which is what the basic formulation that we are going to use in our simulation. So, this is about so that is 1876, this is after 1976, and we are already 40 years past this. And you can say the same thing about Kahn's work, for example. It is rigorous, it is very nice, and you can read the paper yourself and you will find that he has put lots of effort to make things clearer. Okay. So, let us look at the approach of both Gibbs and Kahn. So, what did Gibbs do and what did Kahn do to understand the interfaces, and in all these cases we are interested in a solid liquid interface. In the Gibbsian approach, you can even make it very generic. So, you have two phases alpha and beta, and you have an interface that is separating them. And what Gibbs does is to give a differential form for internal energy that includes the surface term. Okay. And the objective in the Gibbsian approach is to give an adsorption equation in differential form. You will see what it is. Okay. And to do that, Gibbs constructs an imaginary surface that divides these two phases into alpha and beta phases. Right. This is a classical thermodynamic approach which we do, for example, when we discuss the stacking fault energy. This is what we did, right. We said that okay, you have one grain, you have another grain, and you have a stacking fault, or one region and another region separated by a stacking fault. So, we take the system without the stacking fault and we take the system with stacking fault, we take the difference, we attribute it to this planar surface called stacking fault. Even though you saw that it is a region which is looking like HCP, I mean strictly speaking there are two layers which are like AB, AB or BC, BC kind of stacking. But we assume that somewhere in between that there is this imaginary surface which is the stacking fault, which gets attributed all these excess properties. The excess Gibbs free energy is the property of that interface. So, that is how we deal with it, and that is what the Gibbsian approach is. And there is a nice commentary on this paper of Kahn about the thermodynamics of solids and liquids by Larche in the selected works of John Kahn. Some of this comes from that paper. So, what Kahn did is to give a differential form for internal energy that includes the surface term, but he used Gibbs-Duhem equations for the phases that are forming the interface, and he showed that you can use Gibbs-Duhem and you can get rid of this Gibbsian surface construction, right. So, his point is that you do not have to construct this imaginary surface and attribute properties to it. You can use Gibbs-Duhem, and that condition helps you avoid defining an interface as a surface of 0 thickness. You have a diffuse interface, I mean that has been Kahn's contribution to consider that interfaces should not be given any arbitrary width. That has always been his philosophy, and so following that philosophy, okay, so interface has a definite width, but you do not have to know what it is. As long as you have a way of consistently evaluating what that interface property is, you are through. And Kahn's approach is to use Gibbs-Duhem to get rid of this arbitrary construction of 0 thickness interface. By the way, in classical literature, if you see, after Gibbs there have been people who tried to give a specific width to the interface, right. You can assume that it is 2 layers, for example, you can assume that it is n layers, for example. So, there have been interface thermodynamic models which assume given number of planes. It does not have to be 0 thickness like Gibbs, you can have definite width, but can we get rid of this completely? I mean, can we not specify any arbitrary width to the interface? The answer is yes, and Kahn shows how to do it. Because this Kahn's other important contribution, which is also important, is to identify that interfacial properties, when you talk about solids, also become dependent on orientation. In crystalline solids, if you have different planes, they do not have the same property, which means if you have a melt with different planes of the crystal in contact with the melt, the properties are different. Okay. So, this is the interface orientation dependence, or the anisotropy in interfacial free energy, which primarily derives from the internal energy. So, there is a simple bond breaking model you can make. One tends to think that at higher temperatures the entropy would make everything isotropic, and but you can see that in the case of even solid which is near melting temperature, right, solidification scenarios, the anisotropy still shows up, and in some cases it can be very important. So, you have to think about anisotropy and how to incorporate it in the model, that is one. And in a solid there are two ways in which you can increase the interface area. Okay. So, suppose I have some amount of interface, I can add more atoms and make more of the interface, and that will be one way of increasing the area. But in this way of increasing, the interfacial energy per unit area does not change. The total interface contribution increases because we have increased the area of the interface. But there is another way, you can keep the area same, but you can change the interfacial energy per unit area. It is possible only in a solid because it supports non-hydrostatic stress, right. You can have a interface which is elastically deformed, for example. So, its area you can maintain the same, but the contribution that will come from the area, that from that area to interfacial energy will change. In other words, the term that we add, the excess free energy, can be considered as area times gamma, which is interfacial energy per unit area, which was used this morning also for the simulations, right. There was a interfacial energy gamma alpha beta, but that is interfacial energy per unit area. You multiply that with the area, you will get the total contribution that is coming from the interface. Now, if you take a derivative, d of gamma A has, you can use chain rule, it is A d gamma plus gamma dA. Now, d gamma, if you cannot change the per unit area interfacial energy, which is the case in fluids, right, surface tension for example, you cannot change. I mean, you try to put more atoms and then it will again come back to whatever minimal area it is trying to do. I mean, in fact, that is how in elementary school you are taught why surface tension comes about, right. These atoms are sitting and they have these bonds which are not satisfied on one side, whereas bulk they are all satisfied. So, this excess is what results in surface tension, you have been told. That is not the case in solids. So, there are two ways, and they are called accretion and stretching. Accretion because you can increase the interface region, so you will have excess interface energy, and stretching because you can change the bonds that are there in that interface. In solids it is possible. So, there are two ways in which you can increase the interface contribution. One corresponds to d gamma, other one corresponds to dA, and they both have to be accounted for if you are looking at a solid. Anytime you are looking at a solid, especially in this case where we are looking at a solid in contact with a fluid, its solution, a melt, some other fluid, it does not matter. So, can we obtain a generalized adsorption equation in differential form which accounts for this anisotropy as well as these different ways of changing the interface contribution? Those are the questions that are addressed by Kahn in this very nicely written paper. It is a long paper, but very nice paper. So, what we have been discussing, that the solid surfaces, surface tension, which is defined as the energy required to increase the area of the surface by some dA amount. That is how it is, soap film was shown and it moves by a force by a dx, what is the increase in area, and that is how surface tension was defined in elementary classes for you, and that definition is no longer valid in the case of solids because they can support non-hydrostatic stresses. So, we need to introduce this concept called surface stress, which is also an old concept. Some pioneering work was done by Herring, and his papers are also very nice to read. I would strongly recommend, there are a couple of them, surface tension as the driving force for sintering or something like that, in one of the American Metal Society conference proceedings. That there is also a paper by Mullins, there is another one by Frank and so on. So, but Herring has some really nice papers. In physics literature, this equation is known as Shuttleworth equation. I will show what that equation is. And I found when I was preparing these slides, this is slightly old work, I mean few years ago we have been looking at it. I found that Nicholson also had this concept explained. So, in the case of surface of a solid, there can be strain, there can be change in area. Okay. You can strain the surface and keep the overall surface area the same, but it is a strained surface, or you can keep the per unit area interfacial energy the same, you can increase the surface area. So, these two processes are indistinguishable in a fluid, okay. There is no difference between them, but in the solid there is a difference. So, we call the excess energy is surface free energy, and it has two contributions. One is equivalent to what you would call a surface tension, and in the other quantity which is because of strain, because this is free energy change and strain is a tensor, second rank tensor. So, the change in free energy with respect to strain, if you take, it is a derivative of free energy with respect to a second rank tensor, which becomes a second rank tensor itself, which is equivalent to stress, because it is a derivative of a energy with respect to strain, which is what we call as surface stress. Okay. So, there is this surface free energy, which is like the surface tension, and which is the surface stress, which is because of the deformation of the surface. And surface free energy itself can be anisotropic, it is no longer isotropic like in fluids. So, these are the three things that we need to keep in mind: anisotropy, and surface energy, and surface stress, or surface tension and surface stress. Okay. Now, what is the problem in defining a surface stress? You can see the moment something is strained, the reference frame becomes a problem, right. You can define everything in the original frame of reference, or you have to define things in the current frame of reference or material frame of reference, or Lagrangian and Eulerian descriptions. Okay. So, area of solid fluid interface measured in the reference state of the solid, let us say when the solid is in contact with the fluid, and there is one area that you measure in the laboratory frame of reference. These two are to be related through the strain, because in the reference frame there is no strain, in the actual case you will see a strain. So, there has to be a relationship which defines how the surface area measured in laboratory frame of reference is actually related to the original area that you had in the reference frame, which means every surface quantity can be defined either with respect to the reference frame or with respect to the Lagrangian frame. Okay. So, every quantity can be defined twice, and Kahn goes on in the solid and fluid surfaces to define and show the relationship between them. Here, for example, the area relationship is shown. Area plus area times the strain will basically give you the area that you would measure in the laboratory frame of reference, and so on. And when you make this connection for the interface energy is how you get this so called Shuttleworth equation. Okay. So, you can think of Shuttleworth equation as nothing but the stress that you define in the two different frames of reference. Okay. And that equation which is there in spatial coordinates Fij is sigma h delta ij plus dou sigma h by dou epsilon ij. This is known as the Shuttleworth equation. Okay. So, what are we doing? We are stretching the surface reversibly at constant temperature, chemical potential and area. The work done against the surface stress results in the change of sigma. So, this is, I mean, you can see you are taught to that take a small film, stretch it by a force x, f by dx, and so f dx is the work done, which is equal to surface tension. That is how you defined. Now, you have to define it little bit more generically, because now it is sigma dotted with epsilon. I mean, that is all, there is no new thing that we are doing, and this is known as the Shuttleworth equation. So, let us look at thermodynamics of surfaces and let us start with fluid-fluid interfaces. Most of what needs to be done is there in fluid-fluid interfaces, and then when we introduce solid, we know what the differences are. There is anisotropy, there is surface stress. Okay. So, it is easier then to develop this formulation for fluid-fluid and then change one of the phases to solid and look at solid-fluid interface. So, for planar fluid interfaces, the change in energy, this expression was written except for the sigma dA, right, TdS minus PdV plus mu I dNi summation over I, where how many components are there, pure, that is just mu dN, and binary mu A dNA plus mu B dNB, and ternary mu A mu B mu C and so on. Okay. So, sigma is nothing but the change in internal energy when area is reversibly increased while you are keeping the entropy volume constant in a closed system. You are not adding any more atoms. So, dN is 0 and volume you keep constant, PdV is 0, entropy you keep constant, TdS is 0. So, dou E by dou dA, dou A will give you sigma, right. So, this sort of tells you what is the definition of interfacial energy or interfacial free energy is in our scheme of things. Okay. At equilibrium across a planar interface, the temperature, pressure and chemical potentials are constant. Okay. Now, in this you have probably been taught that there are intensive quantities and extensive quantities, and Ferdi also mentioned that you can have extensive quantities, but you define them with respect to per unit volume or something, they also become a constant. So, this definition, the per unit volume quantities do not scale with volume. So, there is a more refined definition that is described by A. Griffiths, I think, do not think it is David Griffiths. So, there is a paper in which there are two kinds of quantities that are defined. One are supposed to be force like, because we are trying to make this analogy between F dx as the work done, right, and the other one is displacement like quantities. There it is shown that intensive quantities are typically what is called as intensive quantities are force like quantities, they are temperature, pressure and chemical potential, and the other quantities which multiply them to give, this is a PdV term. So, the rest of them should also be energy. So, TdS, so ds is the sort of quote unquote displacement for a force which is quote unquote temperature. So, they are defined as force like quantities and displacement like quantities, and you can see that that is what it is, that is why sigma dA. Okay. So, you can integrate the equation, you will get this E is Ts minus PV plus mu I Ni summation and sigma A. And so, you can define sigma as 1 by A E minus Ts plus PV minus summation mu I Ni. E minus Ts plus PV is the Gibbs free energy and summation mu I Ni is the change in Gibbs free energy of the material if the material is reversibly inserted from a reservoir. So, sigma is nothing but the excess free energy associated with the interface, specifically it is excess Gibbs free energy. This is very important because later you will see there are some identities that this interfacial energy has to obey, which is only for Gibbs free energy it would obey. You can't define a, why can't we define an excess Helmholtz free energy associated with the interface and call that as a Helmholtz interfacial free energy? There is no such thing. Okay. So, you will see. So, these two equations that we have written, the energy which you integrated and got and defined as the sigma as the difference is valid for the entire system, right. This is valid for the system in which we have alpha, beta and an interface. Okay. That is how the sigma is there. If there is no interface, that will not be there. Now, if you look at this quantity only for the alpha phase or beta phase, they are equal to 0. right. For homogeneous system where there is no interface, you should get the interfacial energy to be 0. So, if you substitute E alpha and E beta, you will get 0 there for sigma. If this is the expression and if alpha and beta they become 0, you can already see I do not have to define an interface as a region of definite width, right. I can go from one bulk to the other bulk, wherever it is bulk it is 0, wherever it is not bulk only you will get contribution, as long as you are dealing with the Gibbs free energy. Okay. So, that is the important idea that Kahn brought to this formulation. Okay. So, bulk contribute nothing. So, if you consider a small slice around the interface which extends well into the bulk, this is very important for those of us who are doing molecular dynamic simulations. You have seen the interface or Monte Carlo simulation, interface is not a plane, right, it is always fluctuating. So, if I have a mechanism in which all I need to know is the bulk of one phase and bulk of another phase, that is easy for me to determine. Exactly where the interface is not, because that is fluctuating all the time. So, I can go from one bulk to the other bulk, and this formulation assures me that I will only measure the quantity associated with the interface as the excess. Okay. So, that is what is shown here schematically. The shape of slice is also arbitrary. There is nothing that says that I should not take a curved region in alpha and beta, does not matter, as long as it is bulk it will give me 0, and if it is not bulk it will give me contribution associated with the interface. Okay. But important point to note is that this whatever within square bracket that I put is an extensive property or displacement like property of the layer per unit area of the interface. Okay. For example, if I put square bracket E, it is the internal energy of the layer per unit area of the interface and so on. Okay. So, you can define the interfacial energy by defining an interface layer which is now no longer give of any arbitrary thickness that we define. It is of arbitrary width, but we are not associating any thickness with the interface. This is arbitrary width that we are assigning only to evaluate the interface excess property. Okay, so, that is what I said, it is not the Gibbsian interface excess, and this expression also tells that it is E minus Ts plus Pv, that form has to be there. So, you cannot really define excess Helmholtz free energy or anything like that. So, the interfacial free energy to be a free energy has to obey this, which means only in the Gibbsian free energy terms you can talk about the interface excess. Okay, so, now you can go back, and this is also a common trick most of you would have done in thermodynamics. Okay, so, you have this E expression, you have the dE expression, and you can combine and you can get what is known as the Gibbs-Duhem, right, you have probably derived. Now, you have to be careful here, because in this Gibbs-Duhem you might think that dou sigma by dou T at constant pressure and chemical potential will give me the entropy. You can see immediately that that expression 18 is wrong, because on one side I have quantity that is evaluated over some slice, some extensive quantity which depends on the slice, and on the other side I have a sort of state property. But what is the problem? What is the catch? The catch is that if you try to change only temperature, keeping the pressure and chemical potential constant, it violates the phase rule. So, if you want to change sigma by changing temperature, you also have to correspondingly change pressure and chemical potential in such a way that things are kept at equilibrium. Okay. So, that is where we use this Gibbs-Duhem, and so Gibbs-Duhem basically tells what is the relationship. If I change chemical potential, how much should be the change in pressure, or if I change pressure, how much should be the change in chemical potential, so that things are all kept at the same way. Gibbs phase rule. This is why Griffith's paper is also nice, and in fact, I came across that in the context of how all these lever rules and all these surface constructions fail when you have elastic stresses, because elastic stress depends on the configuration. you take a precipitate as one single particle, you will get some elastic energy. Same volume if you take in different morphologies, you will get different elastic energies. Okay. So, this construction of a common tangent fails. Okay. There is a nice paper by Johnson where he describes why in elastically stressed solids classical thermodynamic concepts sometimes fail. It is in that context that I came across this Griffiths paper where he talks about this force like and displacement like quantities. Anyway, that is with respect to thermodynamics. Yeah. 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 So, we are going to show. So, you have to actually do a I mean if you want to find out what is d sigma for a given change in temperature, you have to change pressure and chemical potential in such a way that they cancel out, you only recover the change in sigma because of temperature. So, that is basically the formulation. Because of which you can see that depending on which extensive quantities you adjust against each other, you can define many different interface stresses. The path that you take, if I kept P and V constant or P and mu constant, the interface stresses will be different, which is not surprising because we know that if you have a pressure for example or stress for example, the transition temperature itself can shift. So, it is okay. So anyway, there is a Gibbs-Duhem which is equivalent to losing 1 degree of freedom, which is also probably something that you have done. If you have done materials thermo, these things are done for you. So, we just do some linear algebra now. We have 3 equations and we solve and it gets us. So, the algebra is a little bit involved, but you can do it, it's still not very difficult. So, you get in Kahn's version, if you want to get the change in free energy, then you have to keep, you can keep any 2 of them constant, right. I mean x and y are from S, V, N, I. You can keep any of them, any 2 of them constant, then the change in the sigma because of the other variation will come out in this matrix form. Okay. So, this is consistent with phase rule because you are changing P and mu in such a way that you will still lie on the same plane and so you can evaluate d sigma with respect to dt for example. Okay. So, this is the version of Kahn and he as of now we have done for the liquid interfaces. I did not talk about solids. Okay. Now, if you bring in solid, you can see you had only S, V, N, I here, right, it is a liquid interface, but I said that solids can support stresses, which means in 3 dimensions I will have how many more components, independent components that I can vary, the components of the surface stress. And because in 3D surface is a 2-dimensional object, there are epsilon 1 epsilon 2 and epsilon 1 that you can change. Okay. So, you have to also include, that is what is written here. So, d sigma now also involves f alpha beta epsilon alpha beta. Remember in 3D you have a surface which is 2-dimensional. So, surface stress is a 2-dimensional object. So, if you are in 2D it is 1D object. Okay. So, it is the moduli associated with the surface are not 3 to the power 4, it is 2 to the power 4. Okay. So, that is what is written there. Alpha runs over spatial components 1 and 2 because they are surface tensors, beta runs over the spatial components. And what is this chi? And chi is also something that Kahn introduced and even Herring has, but Kahn tried to do this is called vector Kahn-Hoffman vector, right, it is called Kahn-Hoffman vector. So, they tried to give the description of the interfacial energy by taking into account the orientation effect, and this chi is basically Kahn's Kahn-Hoffman tensor or vector which describes the surface orientation. Okay. So, Kahn ends the discussion in this paper at this point. He says, okay, we looked at liquid. In the case of solids, there are two things. One is the anisotropy of the interface, which can be taken into account by using this psi, chi, whatever, and the second one is the energy associated with the interface. So, that is some stress times strain, surface stress times surface strain, that is what he has written. Now, we know that we can not only keep the S, V, N, I constant, but any of these quantities as constant, and we can do the calculation. Of course, the simulations we still did the easy way, that we took one interface at a time, 1 0 0, 1 1 0, 1 1 1 and so on. So, the any change in the interfacial energy is accounted for by itself, by not taking this into account, but at least the epsilon 1 1, epsilon 2 2, epsilon 1 2 etcetera you can keep constant. You have to keep constant if you are taking a variational partial derivative, okay, and that is where the problems are. So, that is what was done by Frolov and Mission in 2009. They took a single component solid with its melt, I think it is copper or nickel, Sushil, Frolov Mission first paper, copper. I think they also have for nickel. So, they had for several FCC materials, they took the solid in contact with its melt and they non-hydrostatically stress the solid, and the notation that they use is a bit different. Whatever I called Fij, they call tau ij, whatever is called sigma h in Kahn is called gamma and so on, and they call the bulk stress as tau ij, that means sigma ij, but I was calling sigma as the interfacial energy. So, there is some translation of notation you have to do if you read Frolov Mission with respect to what we have done so far, but it is not very difficult. So, they take a solid melt system and what do? They make this bulk solid and on either side you have bulk liquid. We found it easier in simulations to do two bulk solids and in between bulk liquid, and there are these phase equilibrium conditions, which are the same ones I saw. ES is Ts minus PV plus mu n etcetera. I have just brought it to one side, and the interface free energy at solid liquid interface will be given by this expression. And you can write the adsorption equation. Remember that had always been the interest, to write an adsorption equation in differential form, which tells if you change T temperature so much, what is the change in interfacial free energy and so on. So, that has been the aim, and you can do the same thing. Now, you have extensive variables as E, S, V, N, and you can choose any two from these independent variables T, P, mu, epsilon 1 1, epsilon 2 2, epsilon 1 2. You keep it constant and then you calculate the. So, the change in free energy, interface free energy differentiated with respect to epsilon is basically the surface stress. So, Fij is the surface stress, but it can be evaluated in many different combinations, keeping Es constant, Sv constant, Vn constant, Ne constant, whichever way you want, okay. And all of them will lead to different kinds of T constant, P constant, or T and mu constant and so on. So, all of them will lead to different stresses. Just to give you an example, you can take V and N to be the extensive variables which you will adjust against each other, so that you will derive a surface stress, okay. And this is called isothermal path, okay. And you can write expressions, these are all there in Mission and Frolov. And you can do another one which is called isofluid path, and the independent variables are T, P, epsilon 1 1 and epsilon 1 2. We keep N and tau 2 2 plus P times V the constants, okay. So, this after this is algebra, you can keep on taking different things constant and come up with different paths to evaluate your interface stress, okay. So, now we come to molecular dynamic simulations. Now that is the formulation, we know how to adjust the other parameters, so that we are on the Gibbs phase rule is obeyed, we are on that surface, and then you want to evaluate the interface stress associated with the solid melt interface, and because Frohlo and Mission did it for lots of FCC systems, we decided to do it for a BCC system. So, we took BCC iron in contact with its melt and we decided to evaluate what is the interface stress. So, to do that, in the atomistic simulations you have the interface to be diffuse, and this schematic is there in Porter and Easterling. Okay. Solid liquid interface you look at, solid melt interface you look at, if it is a rough interface, then what sometimes you call mushy region or whatever. So, there is a region over which if you go from solid to liquid, you will see that it is an interface, and there is an always excess energy associated with these diffuse interfaces. So, you need to integrate over this region to evaluate this excess quantities associated with the interface. Typically, we are interested in energy, and this other images that you see from, you do not see the bottom, this is from Frohlo Mission's paper. Okay. So, we did MD using lamps and 10 by 10 by 120 units, and we used EAM potentials. There are several that are available for iron, and I think one by Mendeleev et al. From 2003 is what we used, and it is periodic in XYZ directions. And we also evaluated the elastic moduli after evaluating the melting temperature. Okay, I have removed the slide. You have already seen how I evaluated the melting temperature using this potential energy method. That was a nice slide. I will add it when I put it up. I do not know why I removed it. There are so many interface stress presentations. I do not know. You think it is there later? It is there later, okay, fine. Okay. Yeah, so maybe things got jumbled up a bit. So, we did evaluate the elastic constants and lattice parameters, and why is that important? So, I need to know the melting temperature so that I can establish a solid melt interface, and this temperature could be few degrees different for 100, 110, 111 interface, and our system sizes are small. If it is 1812 and if you are taking 1808 or 1816, either the entire cell will melt or the entire cell will solidify. Okay. So, you have to be really close, so that any adjustment that takes place does not move out of my periodic cell. Okay. So, I only take 120 on that dimension as you saw. So, within that I have to make sure that the system remains as at the solid melt equilibrium. Then I stress the solid, right, and how do we apply stress? We only apply strain in these simulations. So, if I know the moduli, then I know for the stress that I need how much should be the strain I have to put. So, that is why I need the moduli, and I need the moduli at the melting temperature, I need the moduli at some 1810, 1820 and so on. Okay. So, that is why the initial simulation you first evaluate the melting point, then you evaluate the elastic modulus at that point, then you set up a simulation with phase coexistence, then you apply biaxial loads on the solid and it adjusts, and after it equilibrates, then you start taking the data. And what is the data? You saw that all I need is some, remember the square bracket quantities are basically quantities evaluated over the interface, and I have already told you that as long as I go from one bulk to the other bulk, I am okay. So, we just for example calculate the pressure, you know virial is there. So, you can calculate volume, number of atoms and so on. So, those are the quantities that go into my this determinant to evaluate the interface stress. So, that is also clear here for example, right, number of how many of them are in the solid, how many of them are in the, what is the volume of the solid, what is the number of atoms in the melt, volume in the melt and so on. So, these are quantities that can be easily evaluated from the simulation. So, that is what we need, provided I also know where the interface is, so that I can go from one bulk to the other bulk. Okay. That is the other part. How do we identify the interface? That also involves some numerical tricks, which I will teach one of the days, maybe tomorrow. Okay. Okay. So, this is the nice way of doing the melting point calculation, and you know, if you are at the top end, everything melts, and if you are at the bottom, everything solidifies. So, you have to be in the right temperature range where the potential energy remains a constant. I mean, kinetic energy also you can take, because total energy is a constant. So, you will see that it is remaining constant, but this potential energy is how typically it is done, and you see that wherever the solid liquid interface is at equilibrium, then you know that neither the solid is growing nor the melt is growing, which means we are at the thermodynamic equilibrium, the free energies are intersecting at that point. So, that is how we evaluated the melting temperature, which we already discussed, and this melting temperature code is given as part of the paper that Sushil wrote. It is published in Computational Material Science. In the supplementary, we have given this code for melting point evaluation. If some of you need, you can take. I will also upload a copy in the scripts, so you can use it. Then you have to do the elastic moduli calculation. So, this was using the strain deform along different directions, and you try to evaluate the moduli. This has to be done at melting temperature, and so there is an error bar, and you can see that 1820 the error bars are also large, okay. But you can get it done and you will get the moduli, and they show the right trend. With temperatures you expect the system to soften and the moduli to go down, and they do go down. Okay. And then you have this solid melt system, you equilibrate, then you apply biaxial stresses and evaluate the surface stress associated with this system. And we need to identify the interface position, and we need to identify the width over which we will integrate, and that is a tricky thing to do, and that is the script methodology I will talk about. This is called a technique called smoothing has to be used, and this is very common nowadays in many of these data analysis things. You also probably use it without knowing. We realized that any time you take a stress strain data from the computer, it is already smoothened, because the raw data if you take, there are lots of fluctuations, and there are also lots of things like you have zero stress and negative strain, and some strain and the stress is still 0 and so on. So, all this gets smoothened, and there are many ways of smoothing data. One of them is averaging by taking a bin and then run this bin and average and put. So, some of these naive things do not work, and Sushil spent lots of time trying to figure out. We also found a nice master's thesis from Asta's group, is it? Or McMaster? McMaster. I do not know whose group it was, but some Canadian university master's thesis where they explained this process of doing a smoothing very nicely. And so, I will describe those smoothing process also in one of the sessions, because if you do some of these simulations, those are the trickier things you have to know. And the smoothing is like this. Okay. Now, what is there on the top, the figure? So, you have this block, I can bin, right. I can take this, there is melt, there is solid, there is melt, and I can splice it into small pieces. Within that piece, I can take every atom and find out BCC. So, 8 nearest neighbors are there. So, if it is in the solid bulk, I know that at specific directions I should see another atom. That is what is defined as the phi order parameter. Number of nearest neighbors summed over Rij minus Rij ideal whole squared, okay. And this you can do for several neighbors, and you know the ideal crystal. So, when you are inside the crystal, you know the lattice parameter. So, you know, but there is still some noise. You will see that the solid also is showing. Why is that? Yeah, vibration. Basically, you are at near melting temperature. So, even though you expect an atom that is probably slightly away or slightly closer. So, you get, so after binning the data points that you get are all these black points. It clearly distinguishes the solid from the melt. You can see the order parameter is not 0 and the order parameter is quite close to 0 in the solid region. You need to fit a parameter, and that is typically a tan hyperbolic fit. How do you smooth this data and get that fit correctly, so that you can identify where is the interface when it goes from this 1 to 0, somewhere in between this tan hyperbolic where it takes 0.5, that is what I would say is the interface. Remember, that is not important for me in my simulation. All I need to do is to go to this region where I see this constant, where I see the other one as constant. For example, I can go from this central to the other one, okay. Just to make sure that we do not have too much error, we take a region, that is what is shown in this. So, we take a small d about the interface, where the d I make sure that I enter well into the bulk on both sides, that is all I make sure, and that we found is about 20 angstroms. And given that iron lattice parameter is about 2.5, 2.3. So, this is about 5-6 unit cell distance is the distance on either side you have to go to make sure that you are well within the bulk region. If you assure that, then your calculation will give consistent interfacial properties, that is there from the formulation. So, the trick is to calculate these smoothen these curves and identify this. That script is something that I will share with you. I will also show what is involved. I will give you the reference to this thesis and so on. Then that is also a common thing that you will see. Many papers do use this common neighbor analysis to construct this kind of order parameter to distinguish between the phases. Okay. Okay, so we found not 20, 10, okay, total is 20. So, 3 lattice parameters on either side. Fine. After doing all this using isothermal path, we did evaluate. The leftmost figure is for 100 interface, middle figure is for 111 interface, and the rightmost figure is for 111 interface. Okay. And tau 11 and tau 22 are the quantities that we evaluated. And you can see that the interface stress, of course, we have gone from compressive to tensile, and the trend it shows for 100 planes is different from 111 planes, it is exactly opposite. Okay. And the 110 there is a crossover, the tau 11 and tau 22. Okay. We evaluated. We also did some comparison with phase field crystal modeling of the same quantities, because there it is far more easier to evaluate these quantities, and we matched trend wise, given that phase field crystal makes this iron lattice with 2 parameters much like Lj. We thought that this is really great. The trends were the same, but numbers were different, numbers did not match. Yeah. Averaged.
By binning the Z. Okay. So here you are doing a Z binning.
Yeah.
Now, sir, the second part. Now, sir, I want to know that how are you calculating the D? So, like, are you calculating it from that by fitting parameters into that?
No, I fit this binned data to get the curve, which is shown in blue. I do not know if you can see, there is a blue. Okay. That blue line remains constant, changes, remains constant. So, I just need to go to the point where it is same constant on this side, same constant on that side. So, we found that that happens to be about 10 angstroms.
So, like that is by just visually inspecting the data or like just by analyzing the data?
Yeah. You can also do, I mean you can write a short script which will say constant goes, yeah.
So, like you mean to say that we can consider like writing a script where we'll find that width where the value is same.
Yeah, so tan hyperbolic it is almost reached a constant value to almost reached a constant value at the other side.
No, then like I just want to know why this particular functional form that you have taken for f of z.
Tan hyperbolic?
Yeah, so like this particular f of z that so like you are writing fitted with following function to calculate the interface position.
Yeah, we fit with a tan hyperbolic because tan hyperbolic nicely describes this. And there is also another reason, I mean if you talk to mathematicians they will tell you that many nonlinear functional forms in PDEs of the phase field type, the solution is always tan hyperbolic. Okay. You can think of this blue line that I am drawing as the equivalent of a phase field order parameter. Okay. And anyway, tan hyperbolic is a very generic function that is fitted for these kind of interfaces.
So like suppose if I just take some random like a times tan hyperbolic this functional form. Suppose if I take
Tan hyperbolic is the functional form. You are
no, so I am saying that like you have here C1 plus C2 times tan this plus C5 plus C6 and you have all these terms. I am saying that if suppose I just fit a tan hyperbolic, like
you will only get one. See, tan hyperbolic will go from -1 to +1. You have to go to 0 to 1, which means it is 1 plus tan hyperbolic by 2. Okay. But that will only take you from 0 to 1. But you need 1 minus tan hyperbolic divided by 2 because you have this interface going to the other side. You see, it goes from 1 to 0, from 0 to 1 also it goes. The two interfaces I need to fit. You can do piecewise. You can take one side and you can fit to the other side.
sir, so like now sir, like what are you exactly doing? Can you repeat to get that D? You are
So, I fit, for example, on this side it goes let us say 1.3 to some 0.3. I fit it to a tan hyperbolic, so I know where the interface is. 0.5 of tan hyperbolic is interface, and then from there on either side how much distance I have to go to get to the constant value, because it is a tan hyperbolic and very how steep it is decided by that C4, C3 etc.
so first you need to find the CIs. No?
Yeah, by fitting.
Yeah, so for that fitting you are using that entire data.
Yeah, we use the entire data, but you can also use it piecewise. Except that piecewise fitted one will not fit the other side. It will fit one half. You can split the data smack in the middle, and you can use one tan hyperbolic for this fit, one tan hyperbolic for that fit. We are doing both the interfaces only for statistics purpose, by the way. I can also just fit one. I know that it will not fit that side, and all I need is the average, right? I equilibrate and I calculate these volumes and number of particles and so on. That is all I need, is not it? So, why am I doing the other interface? Because I am having periodic boundary conditions, so I need to have other interface. Now that there is one more interface, now that there is data available, I might as well also use that to my average to improve the quality. Okay. The calculation of the interface stress itself requires only one interface between the melt and solid to be established.
So no, like the reason I asked this is because like if so like here you are talking mostly about solid and liquid systems. So
Right.
we are talking about something like a SLE or a solid liquid equilibrium. But many times when we see VLE, which is a vapor liquid equilibrium, we often use the definition of a Gibbs interface where we talk about the density difference and all.
That is where we started. we started with Gibbs, we found what is the problem, why some of those things are, well, from a general thermodynamic point of view, why some of the ideas of Gibbs are problematic, which is related to arbitrary interface thickness that he attributes, and specifically in the case of solid there is a problem, because there is nothing like surface tension, there is also surface stress and there is anisotropy.
I think maybe I misunderstood your question, but here you see this graph which denotes an order parameter. For this case of solid liquid gas interface, again you need some kind of order parameter.
Yeah, so like in that case it is a density difference.
It's a density, right? Yeah? So you could plot a similar thing for the density, which also would fluctuate if you measure it across this gas-liquid interface. You would get probably a quite similar plot, except that you can't apply a stress there. But the basic idea is that you always need a kind of order parameter.
Yeah, but this smoothing and identifying the interface in MD simulations is much more generic. All of them do. I mean, fitting to this functional form is specific to us, or specific to this master's thesis we found, but you have to smooth the data to get the order parameter and identify the interface, that everybody does. There is also David Chuck, is it? Laird and David Chuck? Laird and David Chuck. So, I will talk about those papers also. I mean, we did figure out some of these things by going through some work. We will show what it is. So, if you want to identify interfaces, this is the common: identify an order parameter, evaluate the order parameter, take the data will come out like this. Probably scatter is very high here because we are at the melting temperature, but in any case you will see fluctuations, and then fit it, and fit it after smoothing. Yeah.
This tangent hyperbolic, I think, is completely arbitrary.
Yeah.
You just need a smooth function to
Yeah.
describe such kind of step function. But probably
Yeah,
you
so
could
like
also
this is like almost like a step function only.
it's a smooth.
Yeah, but tan hyperbolic, depending on the parameter that you multiply the spatial parameter with, can go anywhere from one end to the other end to a very sharp one.
You could also use a Fermi function or anything, I'm sure,
Yeah.
which describes such a smooth decay from one value to the other value.
So no, so like if I consider something like okay, so here it comes down, it is flat again, and
Yeah.
then again it rises.
Yeah.
So this rise.
See, the lowest polynomial that will do that job for you is a fifth order polynomial. Why? Because you have to go to a constant value at both ends, and it has to go with 0 slope, and in between it has to change slope, and at that point almost it is like a straight line, right. So, you need some 4 or 5 conditions, that it goes to this value, it goes to this value, it goes with smooth, when it goes smoothly with slope 0, it goes smoothly with slope 0, and in between it changes slope. So, 5 conditions, fifth order polynomial will get you the job done.
So my question was here at this point from this lower end to the upper end where we are rising, you are telling that okay, it is a very steep rise kind of a thing.
These interfaces are generally, even that, see, if you ask somebody, or if I ask you, how wide is a solid melt interface?
So like just for that I need to actually fit a function in that interval where that rise is happening, and then so I was coming to that question only, that why can't I fit a sigmoid function there? That is
Yeah, tan hyperbolic is a sigmoid. It is a mathematical description of sigmoid only.
It's just a C4 which describes the width of this.
It is a sigmoid. That is what I am telling. So, most of the, I mean, math people will tell you that for most of the times this is the sigmoid that you can use, and in fact this is taught as a technique. If you have some nonlinear partial differential equation, substitute tan hyperbolic and see if you can solve the algebraic equation, that will be the solution. So, they use it for all sorts of nonlinear equations. Okay. But in some cases you can actually derive and show that this is a tan hyperbolic solution. Kahn-Hilliard and Allen-Kahn equations are of this type, where you can analytically show in 1D, not in multiple dimensions. In 1D you can show that the solution is for these boundary conditions, that it goes to constant and goes with 0 slope, etc. These are the solution. So, these are sigmoids only. So, but our aim was not really capturing the interface. Our aim was to know where is the bulk, how far I need to go away from what I identify as the interface to make sure that my calculation is pakka. The formulation tells that if I go from one bulk to the other bulk, I will evaluate the interface property properly. So, I just need to know where this bulk is, where that bulk is.
Sir, but like when you say that you are doing interface properties,
Right.
you will be studying the trajectory of that interface only, na? So like what I
No, these are like interface stress. I mean, that is what we are calculating here,
no, sir. Okay.
or interface energy.
Okay. Okay. So for that you need to like identify two bulk phases. So that is why you are finding the
Yeah, the formulation tells me that if I go from one bulk to the other bulk, the whatever is in the bulk region, they will contribute 0 in my formulation to this interface excess. Only in the interface region they will contribute. So, the only way I will get inconsistent results, like obviously interface stress should not depend on what width I take for the interface. That will happen only if I start from one bulk and I went into the other bulk. If not, I will leave out some portions which are part of the interface, but I did not include. That is why I need to start from bulk to another bulk. The fear would be that if I go more and more into the bulk, bulk is contributing a lot to this integration. The formulation assures me that that does not happen because of Gibbs-Duhem. That is what we derived and showed. Okay. So, this is the values, and we compared with phase field crystal results, and we were quite happy with the results.
Why is tau 1 1 not equal to tau 2 2 in the middle?
In the 110, the first one is the same because 1 1 and 2 2 are exchangeable, because it is cubic, and in 1 1 1 plane, there again I think there is symmetry that this 1 1 and 2 2 are the same, but that is not so for 1 1 0 plane. So, we see that.
Given so far, or did it just
The planes, no, I have not written. So.
yeah.
Okay. So, what we did is to derive a rigorous thermodynamic formulation for evaluating interface stresses, and like I said, I mean it starts from 1876, people have been looking at, and near about 40 years ago the formulation came, and near about 10 years ago this formulation finally got implemented with atomistic simulations to evaluate interface stresses. You can see that this formulation can now also be used for solid interfaces, right. You can evaluate interface properties, except that you cannot do molecular dynamic simulations. If you want to see the interfaces, you have to do Monte Carlo simulations, and of course, this has been done again from mission. So, he took some MEAM potentials and some nickel aluminides, and he created solid interfaces, did some semi grand canonical Monte Carlo simulations on that, and using similar formulation you can derive the interface properties. Okay. So, it says isofluid path is in progress. I think it is still in progress. I do not think we have done. So, but these things can be used as inputs to higher level models if that is of interest. Okay. So, I will stop here unless you have any questions or clarifications. Because MD does not allow for diffusion to happen. It will never equilibrate, yeah. Or it will equilibrate, I mean it will reach a stationary state, but that is really not exploring all possibilities. Okay.
And this MC calculations you mentioned, they are done on a non-rigid lattice, or?
I think he used MEAM potential. It is not really non-rigid lattice, but with It should be coupled with MD also, right? I don't remember the detail how he did. Yeah. But it was an MEAM potential, which means that it can be away from lattice sites and he will still be able to evaluate the interaction parameters. So. Okay, so there are no more questions or clarifications. I will stop here. I don't know how long I took.
Yeah, I want to briefly introduce to this Ovito visualization software. Which I think in some respect is very similar to this other viewer, ParaView, but I think it has some more possibilities to evaluate data, and I suppose that these order parameters were obtained using the Ovito. So I think we said it in the introduction, if you download Ovito from the repositories as a Linux user, you only get a restricted version. If you want to have the full version, either you pay or you download the sources and compile it yourself. This is completely legal. I checked the copyrights and so on, so it's no problem about it, but requires some extra effort. But I think it's worthwhile. And like always, I think you can also start it somewhere using your mouse, but I prefer to do it by this terminal. So the first thing is you have to load a file. It's done here. And perhaps I start with my lumps examples. So which one did I use? This one here. So you can load a configuration file. There are different file formats, and again, this Ovito is quite general. It normally recognizes the type of file format. We can have a look into this file here. Oh, maybe I should. So this tells you a couple of things, this input format, but it's, I think all the file formats are human readable. So this file contains 45 different time steps. Here a number of atoms of 177. This was for this nudge elastic band calculation. Then you have your box coordinates and the atom coordinates. I think these are the atomic numbers, that's the atomic type, and these are the coordinates of all the atoms. So that's simple, and even if you have another software, you can easily convert your data into whatever format Ovito can read. So the first thing, of course, is you can nicely rotate it. That's simple. Next thing is you can load another file. It was this one. And here it now asks whether I want to replace the graph I had before or whether I want to add it. In this case, I want to add it because I want to have these neighboring atoms plus, so to say, the matrix. And if you remember, this was this trick in this nudge elastic band that you slightly draw these configurations through the crystal. Now all is in red. We can, I think it's here, can make one of them blue, like this one here. Okay, now we hardly see these other ones, so we can, and most things are done here, took me some time to figure out, by this small button, add modification. So I can have a look into it. So here you can do a lot of data evaluation. I think that's even not all. I think it's continued down here. So what we can do, the first step, can put a slice into it. Now you see this interior part, you see the outer part, and you can also slice the other one. For this you have to go up here. Again, this took me some time. Many buttons are a bit hidden, I would say. Yeah? So you can go here and now switch this one to the active. And again, you can put the slice here, like this. Yeah? Or you can put your slice somewhere further out here, or this cutting surface, like this. Yeah? You can switch back and forth between these two groups of atoms. So this is, I would say, simple. For the slices, you can even choose a finite width. Of course, you can choose different normals here, 100, 111, 101, and so on. You can use a slab width here, I think 10. I think these values are in box coordinates, so I think I used like 8 by 8 by 8 atoms here. So I have a slice here. Okay, this was not very clever. I should revert this. We can even switch off here if we remove this little hook here. I wanted to go to the other one. Now I say again slice. If you click on this and you make a slab of probably 4 is sufficient. Now you see here, you can precisely see what it is. I don't know what these blue and red atoms are. Probably these are atoms. I mean, I just took these configuration files arbitrarily, so maybe these are for different steps or so. Okay. So this is very simple, I would say. We can have a look into another file, which perhaps shows a bit more. Did not note which one. I think it was this one here. Now I want to replace it. This file is called dislocation, so I suppose there is somewhere a dislocation in it. I don't know where. So we can try to find the dislocation. Maybe I took the wrong one, I don't know. Let me see again. This one. I think the other one is without dislocation. This, I guess, is... Huh? But it's not so easy to identify a dislocation here. So we can add one modification here. And one of these...
top dislocation analysis.
Yeah, that's one possibility. This I'll show later. I wanted to do this common neighbor analysis. What's this common neighbor analysis? You identify the vicinity of each atom. That's not the, that's the initial point. It's a non-relaxed dislocation. I did a relaxation, I show it in a moment here. So that's a dislocation here. We can do this analysis. And what this modification, as we call it, does is for every atom, it checks the surrounding and whether this is closer to FCC, BCC, HCP, or icosahedric, or nothing of these. This is other here. There are different ways. I'm not sure which one or what they precisely mean, but here you can define a cutoff radius. This is the size of this area around this atom. So This is the initial structure I used, and then I had it running. I'm not sure which one it was. Probably one of these dump relaxes. Stupid, I have not noted it here. Yeah, so this is the crystal after some molecular dynamic steps. Can do the same. And here you nicely see now. How can I rotate it? Okay. What do we see here? We have here the dislocation, which is now spread over a certain region. And here in the center, and if I use the other algorithm to do this common neighbor analysis, I think it's getting even more pronounced. Yeah. What is it here? It's a region of HCP. And that's just a stacking fault in a split partial dislocation, or in a complete dislocation which is split into two partials. I use the dipole here, and I'm not sure. I think I put the dipole already here in this 45-degree configuration. And this should be also the stable configuration for a dislocation dipole. So that's one evaluation one can do. We can also do this. I think there's even more one can try. Maybe I do it. There's the centrosymmetry parameter. Oh no, this is not plotted here. I think one has to then add a color here. Here. Now I can choose the centrosymmetry parameter. The centrosymmetry parameter is a bit similar to this common neighbor analysis. You sum over vectors, just plus and minus, yeah? And then you do it over all the neighbors. So if it's perfectly centrosymmetric, this adds up to 0. If you are somehow out of symmetry, then you get a non-zero value. And again, here you see this varies between 0.2 and 8, and you can attribute colors to it. You can also use this automatically adjust range, which was already done here. You can choose other color codes if you prefer, like this or something else. So again, we nicely see the stacking fault where the centrosymmetry is somehow perturbed. In the FCC lattice, the centrosymmetry should be perfect or close to perfect. At the edges or in this core of the partial dislocations, I don't know, the centrosymmetry is not that bad. You can always switch on and off these evaluations. Perhaps I switch it on again. You can also often plot the values. Let me see, I forgot how it was. Centrosymmetry. Go here. Here you see. So you see how many, here you see for a certain centrosymmetry parameter, how many of the atoms have such a centrosymmetry parameter. Sometimes it's even easier if you look here. Here you get this graph a bit larger, or you can do here, you can identify particles. For example, you can click on particular particles if you use this button here, which is also not very obvious that this button is to choose one particle. So if I click now Now let's first click on some particle here. You see that the central symmetry 0.3, so this is pretty close to 0. If we go to this one here, you see a 7.5. So point by point you can identify, and if you have slices or so, then you can identify these types of defects and find out what really happens here. And then who already proposed that we could use this dislocation analysis. This can be done here. It takes some time. It really tries to do a burger circuit around certain positions. I don't know precisely how they do it. And again, I think we can tip here.
You can just pick their defect, mesh and dislocations and so on.
Which one? What?
The defect mesh and particles you can switch off, then you will see the dislocation lines.
Okay.
The visual elements on right top.
Ah, here, yeah, okay.
So, and the particles also.
Yeah, but then we have only the dislocation. Ah, okay.
You will see the lines.
Ah, yeah, okay, this I did not know. I wanted to show something else because maybe we can keep it also like this. It gives you also the bogus vector. I'm not sure whether, no, it works not in this. So we have to visualize the particles. I think then it, here. Okay, I even don't need to click. Here you see the bogus vectors. We can switch off the particles here. We have these 4 partial dislocations. They're splitting. Yeah? And the partial dislocation bogus vector is 1, 6, 1, 2, 2, 1, 2, 1. There's different signs here, trailing in the leading partial here. If you check, they add up to 1/2, what is it? 1, 1, 0, but I don't know which one. Yeah, so here some is 0, some is 0. No. I don't know which one is which one. Can we click on?
Spatial, the head coordinates and tail coordinates are there at the end of that line.
Oh yeah, okay,
So you know which one is.
right. So you can find out which dislocation is which one in this graph here.
I think you will click on at that position, highlight there.
Huh?
Click the Burgess vector. In
Yep.
the box.
Okay, so that's this one. Oh yeah, okay. I was a bit confused because these two, they are not adding, I think they are adding to 0 or so, yeah. But these ones here, this adds to this and this adds to -3, this plus this adds to +3, and this is 0, so that's 1, 1, 0. So that's what we expect for a complete bogus vector. So this is already quite powerful, I would say. What else do we have for these dislocations? I don't know whether there's more. You can load another file. And this is my homebrewn Fortran software, which has no standard output format. At the time when I wrote these codes, memory was very valuable, so I tried to make it as compact as possible. So I put 1 bit per atom. Yeah, it's just 0 or 1, so that's sufficient. But I have conversion routines, and then you can put it into a XY format. XY format, perhaps I can show again. what it is. As the name says, it's the simplest file format we can use. It's a number of atoms here, 400,000 B atoms. Here you have the atom type, which is 1 for all my B atoms here, and these are the coordinates in x, y, z. Of course, one could make it a bit more fancy, but for me it's sufficient. And then it recognizes that this is not a very standard format, so it asks the software, is the first column indeed the particle identifier? Yes. The second one a position, third one position, fourth one position. I can say OK. I want to replace this one. You see the loading takes some time. Reason is that I stored the whole Monte Carlo run in one big file. Yeah? So these are these 50 times, I think this one was from 0 to 49, so it's 50 different configurations. We can scroll through it. I think this was at a pretty high B concentration. So we can switch to another one, which is perhaps a bit more interesting, lower B concentration. So you already see it's a lower B concentration. It's now 100 things, 100 time steps. And here you see nice precipitates which formed. And now we can check. They also have a cluster analysis. Okay, and it identifies the clusters. Then we can look at a cluster table here. And like before, we can click on one cluster here. Oh, it's probably somewhere down here. It's a huge table, so I don't know where this one is.
I think if you click on that line, it will highlight there in the image. No?
Which one?
If you click on any of the lines, it will not show which cluster it is, like it did for dislocation.
Yeah, that's what I tried.
No, here, if you click on the bottom line.
Ah, here you mean? I think.
Where it is?
No, I think it does not. But of course, you can try to find out the coordinates.
Yeah, position is given, so like 0.5.
Right. But there is more. I mean, here show a list of clusters. So this is what comes out from the Sorschen-Koppelmann algorithm. Here's the cluster identifier, the cluster size. Here they even nicely ordered in size. And I think you can also have a graph. Was it this one here? Here, that's the size distribution. Here is a function of cluster size. What else can we do?
Save that plot.
Hmm?
You can save that plot also.
Yeah. This I'll show in a moment. Yeah. This again is a bit tricky, but here we can just look at the time evolution. Now you see how this cluster size distribution changes, but be careful, the axis here changes. Yeah, so. And it mostly shows, I think, the subcritical clusters here. For the cluster size, there's also an important parameter which they call the cutoff distance. When Guru explains this Sorschen-Koppelmann algorithm, he assumed that we just go to nearest neighbors. Yeah? If you want to include second neighbors, you go to a larger distance here. And if you go to 5, I think this will not change very much. 5 is not sufficient. Now 5, all the clusters, all the atoms belong to their own clusters. But here, starting from 6, you find nice clusters. And if you go to very large values, 10 is then everything, no, not yet. At some point, everything is connected. I don't know. I had it when I looked at the code here. Here, now they are all connected.
But this is Herschel-Koppelman with periodic boundary condition, right?
I suppose, yes, but I don't know.
If you have a particle that is coming out, it should number it.
Yeah, we can check. First we find one on the edge. Yeah, I think so. Oops. I always have difficulties with this rotation here. Here's one sitting on the side, and I think it's coming in here. I'm not sure whether it's the same color or maybe not. You can also calculate the center of mass for each particle and so on. Then something which might be useful. I did not show one further option. I think you showed just examples where you have these 3 views, X, Y, Z, and then this 3-dimensional view. I don't know, I don't find it too helpful, so I prefer this one. And then you can make it a bit nicer. I zoom a bit in here, and I think it was here. So you can create smooth particles. Let me see, where was it? Construct surface mesh. I think it was this one. And now you see that these particles are somewhat rounded, yeah, here, plus the vicinity around them, 3B atoms close to the clusters or so, I don't know. This might be helpful. Oh, here's a nice one. You see this one? It's nicely faceted. This one here. Gives the impression that the 1-1-1 surface or interface is the lowest energy, so probably it's a kind of equilibrium shape we obtain here. And then you can also do this statistical evaluation. I think it was this one, spatial correlation function. I think it also does. Yeah, it gives the structure factor. Take some time. Oh. Apparently it does the calculation for all the configurations here. Perhaps I should switch off some of the other properties here. It's nearly done, 70%. But mostly, I think what you should take from this little presentation is that this is a very powerful software with so many possibilities. Did it crash now? I switch off all this here. So I'll do it again. Which one was it? Spatial correlation function. Maybe it's too much data, or I don't know.
Yeah, it is 36%.
Yeah, this was, but then it stopped at 90% or so, and it did not crash, but it lost its results. That's why I switched off here all these other evaluations I did. Perhaps it now works. I mean, these are these S of Q, which I showed before in the other talk. Perhaps we give it a moment here. But it's 100 configurations, and for each it has to do the three-dimensional Fourier transform, which is apparently a bit time-consuming.
You have a GPU card?
Yeah, but I think it's
Does
doesn't. I don't know.
Most of these are visualization software they should be using.
Yeah, but I think
default. I don't
it's an integrated. Yeah.
know. Did crash this time.
Okay, there was one more thing I wanted to show. Yeah, here it crashed. Memory fault or so. Let's take a smaller one. Which one was it? 8. If you want to produce a nice movie out of this, yeah, you choose the orientation. I mean, you could here now run the movie. With whatever property during the calculation. So we could use the cluster analysis here. Okay. This input file is not the best. Okay, I try again with this one here. Just wanted to show how to output the data. So if you run this movie here, you see how these clusters evolve in time. And if you want to record it, you go to this camera here. Now you can render either a single frame or the complete animation in a movie of whichever size, 640 by 480. And then you can say save to file, which I don't need here. I thought it's done here.
By clicking on choose, you have to give the path.
Pardon?
Folder file name. Where you want to see.
I have to give one,
You have to
but I wanted to.
open the file.
And here I have to say render active viewpoint. Now it produces here this little movie. And you can also somewhere choose whether it's here every nth frame, so every frame or every second or tenth or so if you have many points. And perhaps this is not so nice. We should go back to this one here and make the particles at least red. I think, I forgot. No. Yeah, here you can attribute colors, particle identifier. Here, for example, red. And at some point one could choose also here a sphere or something else, the size of the sphere, like this. And now we can go back here to this renderer. This looks a bit nicer. Now you see the temporal evolution of these clusters with time. And then we can throw away this one. So that's what I know how to handle. There's much more. Here you see this long list. Atomic strain. If you try this, it's not possible because in the input file we don't have ideal coordinates or we don't have strain coordinates or so. So if you store data, for example in an MD simulation, in an MC simulation you have no strain. But in MD simulation, you can say the MD, the lumps, which parameters it's supposed to store. And of course, what is not available to the visualization software, it cannot visualize. Yeah? So here's this. Then this cluster analysis we had already, coordination analysis. This is, I think, similar to this. I'm not sure. This dislocation analysis, we saw displacement vectors, we did not see. Elastic strain would be interesting in a MD, grain segmentation, I don't know, and so on. Voronoi, you know what Voronoi cells are. So if you have one atom and want to define which part of space belongs to this one particle, so there's a specific construction. Perhaps you know Wigner-Seitz cells in solid-state physics, and it's quite the same. From each atom, you draw a line to the neighboring atom, and then you put the middle plane on perpendicular to this line here. You do this to all neighbors, and then you obtain such a strange body around each particle. You can try. I don't know what it does.
Grain segmentation also.
These
In
are
the deformed system, it will try to show if there is any higher orientation has developed.
okay. So apparently there is a problem about the I don't know whether it has to do with these parameters. So this I never tried, this Voronoi analysis. I mean, for crystals, it's not so interesting. You get the Wigner-Seitz cell. But for amorphous materials, it's interesting to have the Voronoi.
In the add modification, below Voronoi you get the Wigner-Seitz.
Yeah, okay. Oh yeah, yeah, defect analysis. Then you can have different types of coloring of atoms or some defects or so. Here, I don't know here. In particular, we showed this slicing here. Here's this rapid periodic boundary conditions. So probably one has to do this, and then the cluster analysis, then you get connected clusters. You can select atoms. These, I don't know, I mean the centrosymmetry parameter we discussed, the common neighbor analysis we discussed, the rest I don't know. I mean the Chill plus and the Ackland-Jones, you know what it is? No. I think it's probably something from crystallography or so. Here this was to create smooth clusters, create bonds. I don't know what it does, probably it creates. Okay.
So this analysis is specific to like class rates.
I see. So more or less you can do numerous things with this. What I did not find and what is available in the ParaView is labeling.
Time and
Yeah. So maybe it's hidden somewhere, but I tried to find in the manual. So if I run such a movie to present the time here, this is missing, and also other evaluations, perhaps it's hidden somewhere like a cross-sectional line.
you have never tried with this.
I think it's not, or did not find.
So typically we use Ovito with MD,
Yeah.
where we generally don't draw lines. ParaView we use with phase field, where we need to know the composition profile.
So
but
there.
This thing must be here also. The labeling when you make movie, time labeling.
I checked in the manual and I checked here. So here is nothing, I think. Then freeze property, delete selected. Yeah, there's something else. What one can do, you can give conditions here. So for example, you can filter the particles. What was it? X. No. I forgot the syntax here. So you can give conditions here. Position.x larger than 10. Okay.
So apparently there's some viewport layer where you can give text layer.
Actually, the top one, this near the camera, that option is there. That is the viewport layer. Maybe there that option is.
This one?
Yeah. Add layer.
Somebody is saying that viewport layer will add timestamp and
text
other
label.
also.
Yeah, here, source frame. Does anyone see? Here we probably have.
Yeah. There is a text label, but I don't know how to put time. But
So in that text box is there whatever you type and save, I think that will come.
but timestamp, where will it go?
Project vector we have typed and we have saved.
Does anyone see any text here? I don't know which units they use for this text. So apparently there's even this possibility which I did not see before.
Alignment also is the top left or something.
Yeah.
Maybe it is because the black thing you're not able to.
No, I used here a bright color.
What happens if you make it white or something? No, I still don't see.
Text. No, I suppose that one first has to say okay at some point. So that's something one has to look up in the manual. Yeah? So this would be helpful. Okay. I mean, that's something you should try out. And probably it's best to get a bit familiar with both softwares, ParaView and Ovito. Both, I think, are powerful in their own respect. And I think there are others. VMD, I think, is another visualization software, but I think that's less fancy as this one.
There is one called Mayavi, which is based on Python, which is quite powerful. For example, 3D, if you make, on the walls you can project the cross section. You can slide to get the required cross section. And Matplotlib also does many of these things. So apart from this, I found Matplotlib is the other one if you're really interested in doing some detailed analysis. This does very well for dislocations, junctions, and
I mean that's a strong point that you really evaluate the data. That's far beyond just visualization.
Some 3D things work very well in Matplotlib and Mayavi.
Okay.
They are Python-based visualizations.
Okay. So that's it.
For today.
10 minutes past 5. Yeah. Early today.